Thank you very much, Claire. And I must say it's a great pleasure to be here. Thanks for the invitation to play a part in this very interesting meeting. Okay, so azoles. Azoles have been around a long time, and in fact the first thing I'd say is they're really a big success story. Unlike some modes of action, they've been pretty effective over a long period, not just in agriculture but also in clinical medicine. They're used as antifungal drugs, a few examples here, and of course there's some on the right hand side that you'll be more familiar with, if you like, the foundation of many of our fungicide programs in arable crops. But as we know, there have been some issues with their efficacy more recently, and that's what I'm going to be talking about this morning. First, a little bit about how resistance to fungicides, including azoles, develops. Azoles are, like most of the modern fungicides, single-site inhibitors. In other words, they have a target site that they interact with. So here's your fungicide getting into the cell, and there's a number of different ways in which that cell can become insensitive to the fungicide. And the first one is actually the target site itself changes, so that the fungicide no longer binds effectively, or it's less effective. And we'll look at some examples of that in a minute. A second possibility is efflux. The fungicide can actually be pumped out of the cell. And in some clinical situations, this is a well-known mechanism. A third mechanism is actually the target site can be amplified. It can actually be expressed at a higher level than in the sensitive cell, and then that will reduce the efficacy of fungicide as well. And in actual fact, these two alterations of the target enzyme, which in the case of azoles is called CYP51, and enhanced efflux, have been characterized in human pathogens, Candida for instance, whereas in plant pathogens it's usually a combination of alteration of the target enzyme and elevation of the intracellular target levels. Now, looking at azole resistance in European arable crop pathogens, there are a number of examples where we know that the target site changes, which are here, have compromised efficacy in powdery mildews, in Rhynchosporium. There's been some examples in rusts. As yet, no real information on stem canker. But I'm going to be talking about Septoria leaf blotch, where we know that CYP51 mutations are important. That is a change in the target site. We also know that overexpression of the target site can play a part. Efflux is less well characterized, hence I put a question mark. We know that sometimes you can see isolates that do have enhanced efflux, but how much this affects efficacy in the field is debatable. The other case history that I'm going to be dealing with is light leaf spot. We heard this morning that this has become an increasing problem in oilseed rape recently. Therefore, the issue of chemical control becomes important. And I've put a series of question marks here because until very recently, we had very little information on what was happening in terms of fungicide efficacy. Okay, so kicking off with a well-known foe, Mycosrella graminicola, which I'm sure you will more usually call Septoria leaf blotch. I don't think I need to explain to you after 2012 the importance of this pathogen, how it can compromise yields. After the demise of the QOI fungicides, really control of Septoria has relied very heavily on azoles, but we have seen this erosion of efficacy really since about the mid-2000s, and that appears to have been accelerating recently. We do, of course, have the new generation SDHI fungicides coming in, and we need to think very carefully about stewardship of those, which relates again to the use of azoles. Okay, now I think most people will be familiar with these kind of dose-response type curves in terms of populations of Septoria to a number of different azole compounds, tebuconazole, epoxy, prochlorase, and this is the sort of active constituent of prothioconazole. And what this is showing is changes over the years. 2003 is the blue line, so we can see here with epoxy, if we take it as an example, in 2003, this was the sort of sensitivity profile of a typical population, and we know that it's shifted to the right, and in actual fact, the 2012 population here is apparently still moving a little bit. With prothiodesthio, this is a slightly different way of presenting the data, so I should say that it's not as extreme perhaps as it appears here, but we know that there has been a big shift over 2003 to 2012. And with prochloraz, it's an interesting picture because it looks like some of the population has got a bit more sensitive, and that's one of the things that we can come back to a bit later in terms of mixtures and whether there is any virtue in mixing azoles when we know that some of them are reacting differently to others. Now, here's my protein model that I thought I'd include just for interest's sake, the sort of spaghetti version. The reason this is important is to understand what's happened to azoles, we really need to know a bit about the target site. The target site is this enzyme called Sterol 14-alpha demethylase. It's actually present in the sterol biosynthesis pathway, which makes the membrane of the fungus, and when that's inhibited, the fungus can no longer grow. And what we need to know about it is that this is the sort of part of the molecule that interacts with the fungicide, and if this part of the molecule is changed physically, there can be compromised activity of the fungicide. Now, over the last 10 years at least, we've been studying this particular protein, and this is just to explain, this is what we call a sequence of the protein. Obviously, the protein is made up of lots of building blocks called amino acids, and they start at this end and finish at this end. And this is a lineup of different CYP51s, including at the top, the one from Mycosphaerella graminicola. Now, we know that what's happened over time with this protein is that there's been changes taking place. And in the first instance, there was a change at this position in the molecule, and this slide will become somewhat repetitive, I have to say, but I've put it in for a reason, which is to show that unlike the QOIs, where a single mutation compromised their efficacy, what's happened with the azoles is that there's been an accumulation of changes. So that one's as far back as 1988, and as far as we know, we couldn't see really any change in sensitivity caused by that mutation. Then some more came along, Y137F in 1992, for instance, different position in the molecule. Then one over here, one right at the far end of the molecule here, that's in 1993. And we just keep going. This one's quite an important one. There's a deletion here. 2 amino acids were removed in 1999, and it just kept going. 2001, this one appeared, and this is going to be a bit repetitive, I'm afraid, clicking away, more changes. This one down here, S524T, is one which we know has had a major effect on the best azoles. So essentially what's been going on is this protein has been evolving and changing over time under selection by fungicides. And the process continues. And why are these changes important? Well, if you model the molecule, which I showed earlier, this is a sort of magnified part of the active site. This is just the 137 change, which was a single amino acid tyrosine conversion to a phenylalanine. And if you look at this, this is the fungicide binding, and actually this has changed the shape of the binding pocket. And we know now that there is some, what we call steric hindrance, some interference with the binding of the fungicide caused by that change. Now, you may remember triadimenol. I don't think we use it anymore, but it was used widely back in the 1980s and 1990s. And if you remember from that sequence, that particular mutation appeared quite early in the sequence. So actually, while we were using triadimenol, this mutation popped up and obviously was interfering with the activity of that particular fungicide. Interestingly, you can't find that mutation in the population anymore. It's disappeared. So it's no longer being selected for. So it's basically an evolutionary story. Now, the end result of all this is Jonathan did me a big favour earlier by showing his slopes. This is the slope illustrated in a different way, because here we have a sort of chronology of isolates. This is a sensitive wild type, and at the top here we've got epoxy, prochloraz, tebuconazole, prothiodesthio. And where you've got green, to make this easier to interpret, green basically means sensitive. And as you go down in time, 1994 to 2008 isolates, 2009 to 12 isolates. This is showing the accumulation of those changes. So gradually, each group of isolates become more complex. We've got one down here which I think has getting on for 10 changes in the molecule. And then over here we've got the sensitivity values. Yellow means in between, resistance factors, greater obviously than the green. But when we're getting into the reds, this is really where efficacy is being compromised. And we're now beginning to see that actually in the field. And in 2012, which of course was a really big Septoria year, I think for the first time we saw that the elite triazole compounds, epoxyconazole, prothiaconazole, weren't actually doing the business as well as they had previously. And that's to do with this gradual accumulation of changes. One other factor on this slide is that this one here, 50S, 188, 131, 381, the deletion, and N513, it's got those changes. Actually, if you look at the pattern there, it's still intermediate or slightly sensitive. The same genotype, this is exactly the same set of changes, and we've got some more resistant ones. And what we found in this is that actually these have not just the physical changes in the protein, they've also got overexpression of the protein. So there's a change in the amount of the target site being produced. And the combination of those changes plus overexpression has caused a loss of sensitivity. Okay, some quick conclusions from that. With Mycosrella or Septoria, we know that the molecular mechanisms associated with the less sensitive or resistance phenotypes, we've characterised those quite clearly now. The major mechanism is alteration of the target site. There are some additional mechanisms that I just mentioned, for example, overexpression. The changes in the target protein affect all of the azoles, but some mutations affect certain azoles more than others. And that's where this kind of concept of, well, can we use the diversity within the azole class to at least manage the population to some extent? But of course, evolution continues. We have new combinations of changes emerging every season. Okay, so that's the Septoria story. Moving on, we thought it was timely to include something on oilseed rape pathogens, and we've heard already from Bruce about Pyrena persiza brassicae, the light leaf spot pathogen. This is work that was done largely by our PhD student, Helen Carter, who's now working with Syngenta. And as I showed a series of question marks at the start, hopefully this will answer some of those question marks. So here we have the disease. We've heard already that there's been a big increase in recent years. This is the 2012 data from Crop Monitor, a very severe year, and other recent years have been troublesome as well. For control of light leaf spot, traditionally we've used azoles and the methylbenzimidazole carbamates, the carbendazim type fungicides. And in the UK, carbendazim and prothiaconazole are the most commonly applied, or have been until recently the most common applied ingredients. The MBCs I'm not going to talk about in any depth. Population surveys have shown that actually insensitivity to MBCs is now very widespread in UK light leaf spot populations. So we can't rely on them to provide adequate control in all regions. There is some variation, but I think we have to assume that MBC resistance is now pretty prevalent. The situation with azoles, as usual, is a bit more complicated. This just shows tebuconazole sensitivity, the effective concentration 50 values, and these are isolates from pre-2000 that we've had a look at, and you can see that this is back here, this is a sensitive isolate, this is a log scale, so obviously there's quite a big change between these, this isolate here, for instance, and these. So there was some drift pre-2000, but since 2000, this is 2008 to 2011, this has been changing a lot more. So again, as with Septoria, we're seeing a drift in the population. And in actual fact, if you calculate that, that's about a 20-fold difference in sensitivity. So there's something going on which obviously is changing the sensitivity of the population. Well, once again, we had a look at the target site protein. It's the same target in this fungus as it is in all others. And there's a very interesting pattern here because we can find changes in some of those isolates, but not in all of them. So these ones here, for instance, although they're shifted in sensitivity, we can't find any changes in the target site, whereas here we have a change at this position, 508T, which is actually equivalent to 524 in Septoria, and 460S, there's a change in these. So changes are taking place, and it looks like they're obviously contributing to resistance, but they can't obviously be the only mechanism. Now, I mentioned that this overexpression business can take place, and here's some data looking again at isolates after they've been exposed to tebuconazole, so they've been in the presence of the fungicide, and you can see actually after they've been treated with fungicide, they increase the amount of CYP51 expression, and that occurs in these sensitive wild types. But if you look further right, you can see that these ones are got higher levels of expression, but there's a much bigger induction of expression in some of these. And what we found is that in the regulatory part of the gene, the bit that switches the gene on and off, there's been a change. And this is expressed as here an insert. There's an extra bit of information inserted in the promoter of the gene that switches on expression. And these vary in size. This one's 150 base pairs. There's another one here that's slightly different. And then there's a smaller one here with a 46 base pair. And this gives a different pattern when you actually amplify the gene. It's a slightly different size. Now, we know that these inserts are actually linked to increased levels of expression, which does actually affect sensitivity. So again, we've got two mechanisms operating, and sometimes they can be combined. This really repeats what I've just talked about. We've got various combinations beginning to appear. It's not as complex as the situation with Septoria, but obviously it's a moving target, and over time we would expect more combinations of changes to come into the population. So I think this does account for some of the things we've been seeing recently, some field reports of reduced efficacy of azoles in controlling light leaf spot. And it's obviously a situation that we need to keep an eye on into the future. This is just one set of data from one field in Chichester, Sussex this year. And again, a mixed population. There's a comparison with the sensitive type over here, but these are all 2013 isolates, and they vary a bit in sensitivity, but you can see they're all different to the original sensitive strain. So clearly we're dealing with an altered population with a mixture of changes. So to conclude, we now know that this is emerging as a damaging disease in parts of the UK where previously it was not that important. Resistance to MBCs is widespread, and obviously we can't rely upon them. Reduced sensitivity to azoles has evolved. Mostly this is correlated with expression and mutations, although we think there's other genetic factors contributing, which we haven't yet characterized. And we think that what we know about Septoria, Mycosorella, actually can help us perhaps predict what might happen in Pyrena precisa light leaf spot, because many of these changes are actually equivalent to those that we've seen already in Septoria. So hopefully there will be some degree of prediction as to what could happen next. Okay, so I want to finish off actually with a rather different angle on all this, and that's more to do with management and the issues of mixtures, alternations, etc. And we have a link project ongoing at the moment that's actually to do with the SDHIs. This is the title of the project: Improved Tools to Rationalise and Support Stewardship Programmes for the SDHI Fungicides. And one element of this that's been done in conjunction with the partners shown here is actually trying to model the effects of mixtures. And of course, this is being done primarily in the context of safeguarding the SDHIs. But the good news is, so far in the UK Septoria population, we haven't had any instances of resistance that have been confirmed. Therefore, we've sort of turned the project on its head, and we've looked at, well, what happens if you are trying to alter response to the azoles using an SDHI as a partner? So it's almost a sort of back-to-front approach to the project. So here's what we've been trying to do in one part of the project. I showed you that in the Septoria population there's a lot of different mutations, and that some of them actually act differently against different azoles. And this one in particular, called V136A, we know is selected quite strongly by prochloraz and actually quite strongly against it by tebuconazole. So this is where, you know, the prochloraz-tebuconazole type mix may have different effects. So what we've really been trying to test is this hypothesis here, which is the mixture benefit won't depend necessarily on reducing the dose of the azole component, but actually by increasing the SDHI dose, we may actually reduce selection for particular azole-resistant mutants. And we could perhaps improve that effect by manipulating the azole component. But the key thing that we're testing here is by including an SDHI in the mix, can we actually change the selection of those particular fungicides of that particular mutation? So it's really an exemplifying how the mix might work. The design is shown here. We used winter wheat consort. We had a T1 and T2 treatment with either tebuconazole or prochloraz in mixture with actually isopyrazam as the SDHI. The Septoria population was then sampled in July and the frequency of mutations was determined. Now this next slide is quite busy, but I only want you to look at one bit, and that's actually from this site. This is the SRUC site. And what we've got here is the frequency of that mutation. This is V136A, one of those mutations, and you can see here that in the untreated it was relatively low. If you actually treat with prochloraz, which selects for the mutation, without the mixing partner, there's very high selection for that mutation. So obviously it's doing what we predicted it would do in terms of prochloraz selecting for that change. But actually if you mix in your isopyrazam down here at different rates, if you mix it in at a high rate, 1, you can see that selection is reduced. If you mix it in at a lower rate, 0.25, you can see actually there's no real benefit. So it's all working, we hope, in the way that we would have predicted from the initial hypothesis. It's actually shown a bit more strongly if you do the reverse version, which is using tebuconazole, which selects against that mutation. And so here we have the untreated with quite a high level of V136A, but if you treat with tebuconazole without a mixing partner, it's reduced to a very low level, but with the mixing partner, the selection is less. Now, of course, in many ways we would say this is predictable, but I think it's the first time we've been able to demonstrate with a specific genetic change, one of those mutations, in the Septoria population, that a mixture is having a benefit in reducing the selection towards a particular change. And I think that's quite an important proof of concept. It's an ongoing debate. The model predictions were good. Mixtures with the SDHI did reduce selection for mutations affecting azole sensitivity. If the converse is true, and we don't know that yet because we don't have insensitivity to the SDHIs, robust doses of azoles in mixtures should reduce the risk of resistance. And just to sum up, the resistance to SDHIs, there's been one mutation reported in France in 2012 at one particular point in the C subunit of the protein, but as far as we can see, it has little effect on sensitivity. But of course, we need to continue monitoring very carefully to make sure that these absolutely first-rate products aren't compromised by the development of resistance. Quite a lot of people to thank. Obviously, our partners played a very important part in this. This is the fungicide resistance group at Rothamsted. The two real players in this are Hans Kuhls, Bart Fryer, Nicola Hawkins. Helen Carter did the light leaf spot work. John West. Frank van den Bosch is really leading the modelling side that I described at the end there. Partners at the University of Swansea who helped us with the protein modelling, and Mike Shaw at Reading, Neil Pavley, ADAS. And thanks very much indeed to HGCA, who I have to say has been an absolutely vital partner in this work and an important catalyst to get the other partners on board. So, many thanks.
Great, thank you very much. Indeed, John. Thank you.